Okay, Chemistry 3101, let's take a look at a problem. This comes straight out of our textbook. This is the kind of problem that you could face on a quiz or an exam. It says, deduce the structure of a compound with the molecular formula that's shown here. So they give us some information here that produces the following NMR spectrum and carbon-13 spectrum. So the formula is, I'll write it down a little bigger here, it's C9H10O2. So the first thing I would want to do is calculate the HDI. Now the HDI in this case, if you take 9 multiply it by 2, that's 18, add 2, that's 20. 20 subtract 10 is 10. 10 divided by 2 is 5, so the HDI is 5. So now that we've got the HDI as being 5, we know we've got 2 oxygens in the molecule. Let's go over to the proton. Now I want you to have the table of proton chemical shifts with you, and you notice that you have a total of an integration of 1 here, 5 here, 2 and 2 here. If you add up 1 plus 5 plus 2 plus 2, you get a total of 10. So that tells me that this peak here represents 1 proton, this one represents 5 protons, and both of these represent 2 protons. Okay, both of those represent 2 protons each. All right, now you notice that there's a peak here. It's really broad, and it's getting close to 12 parts per million. You can't even hardly see it. I mean, it looks like it's up here, which is around maybe 11.7 parts per million. Could anybody tell me what kind of functional group I might have in this compound based off of the typical values for proton NMR chemical shifts? If I have a shift that's almost to 12 parts per million, it's probably a carboxylic acid, right? So let's write that down, because if you go to your table of values, you saw that a carboxylic acid proton is going to have a chemical shift of around 12 parts per million. Well, there you go. Now we've gotten rid of one of the HDIs, right? So now we're down to 4, okay, because one of the HDIs in the double bond, I mean, you shouldn't do it that way, but anyhow, we've taken care of one of them, really, okay? Now I have another question for you. You notice that there's a multiplet here at around 7 point what? It looks like it's around 7.2, 7.3 parts per million, okay? Maybe around 7.3 parts per million. Could anybody guess what type of functional group would give us 5 protons around 7 parts per million? Based off of the typical values for proton NMR shifts. We looked at them today. What kind of protons come out around 6.5 to 8? Exactly. Aromatic, right? Aromatic protons come out around 6.5 to 8. In the table that I gave you, it says 7 to 8. Close enough, okay? Now, if there's 5 of them, right, that tells me that I probably have an aromatic ring that has just 1 substituent on it, okay? Now we've gotten rid of all the HDIs, right? Because there's 4 units of unsaturation here, and there's 1 here. Okay, so I know I've got an aromatic ring in my molecule, and I know I've got a carboxyl group in my molecule. Okay, now I've got 2 more signals down here, and the resolution isn't the greatest here, so I'll kind of help you out. But these 2, this is a triplet. Okay, and this one is a triplet. Okay? So I have 2 triplets, okay? And they both integrate for 2 protons. Now, how could I have such a thing? How could I have 2 triplets that are both going to integrate for 2 protons? Well, let me tell you the answer right now. If I have a methylene coupled to another methylene, right? If these are both attached to different groups, okay, that means that these 2 protons will be split by these 2, so that's going to give me a triplet. And then these 2 protons are going to be split by those 2, which will also give me a triplet. So it means I would have a triplet of triplets. So now I've got an aromatic ring. I've got a methylene and another methylene attached to each other. And there you go. I've got all of my carbons, all my oxygens, all my HDI accounted for. So the only possibility would be this, where I have the aromatic ring. It's got the two methylenes in the carboxyl group, like that, right? It's the only possibility for this compound. So let's see if this makes sense with respect to my carbon NMR. Could anybody tell me, and I'm not looking at the carbon NMR yet, if I just look at this proposed structure, could anybody tell me how many signals this compound would produce in the carbon NMR spectrum? Or how many signals it should produce? It should produce a total of what? We've got, somebody says 7. I think that person's right, because we've got 1, 2, 3, 4. Check this out. 5, because both of these are chemically equivalent. 6, because both of these are chemically equivalent. And then we've got 7. Exactly. We would have a total of 7 signals. Okay? So if I call this one A, B, C, D, E, F, G, that's 1, 2, 3, 4, 5, 6, 7. Perfect. So I see a total of 7 signals. All right? You see the signal up at G? It's at 179.9 parts per million. Could anybody tell me which carbon that would be? The one at G, could anybody tell me where that exactly? It comes from the carbonyl. That's right. So this would be G right here. I have A and B. It must be these ones. I mean, I wouldn't expect you to split hairs here. I would say, based on my experience, that the A is probably the one by the aromatic ring, because the carbonyl is going to be more electron withdrawing. So I'd say that this would be the B, this would be the A, like that. Then, if you look in the aromatic region, which I said was between 100 and 150, so that means it's from here to here. So these are all the aromatic protons right here, C, D, E, F. Well, you can see that C and F are much smaller, aren't they? Right? They're significantly smaller. That tells me that E and D must be these ones here, right? Because they're twice the size. Now, if you mix them up, if you put E and D, I wouldn't care. Okay. F is probably this one because it's going to be a little more electron withdrawn. And there you have C over there like that. So there you go. We were able to determine the structure of a pretty complicated compound. But what helped us was having the NMR, right? Both the proton and the carbon enabled us to deduce the structure of the molecule, just like that. Let's take a look at something that's maybe a little simpler. And we'll take a look at how do we know that G was the carbonyl? Because if you look at the table of carbon NMR shifts, okay, you see that in that table, okay, down at the bottom, it says carbonyl is going to have a chemical shift of 150 to 200 ppm. So since G is at 179.9 ppm, it falls in that range, and G is the carbonyl carbon. Does that help? Okay, great. Awesome. Awesome. All right. Well, let's back up here and let's try one more problem. Let's try 15.57a. Okay, it says propose a structure for this compound. So we're looking at this one right here. Okay, all of this information. We've got a doublet at 1.09. that integrates for 6 protons. We've got a singlet at 2.12 parts per million. So these are the chemical shifts here. So this is 1.09. This means parts per million, okay. Anyhow, and then we've got a septet at 2.58 that integrates for 1 proton. We've got C5H10O. So that means that we've got an HDI of 1. So we have HDI is equal to 1. Could anybody tell me any of the alkyl groups that might be present in this compound? In 15.57A, if I have a doublet that integrates for 6 protons and a septet that integrates for 1 proton, could anybody tell me what type of alkyl group I might have in my molecule? We looked at it earlier. Isopropyl, yeah. So you must have an isopropyl group in your compound. If you have 3 protons that are a singlet, the only possibility then for these would be a methyl group, just a plain old methyl group. But this only accounts for 1, 2, 3, 4 carbons, and you've got 5 carbons, but you've got an HDI of 1 and you have an oxygen. So that tells you that you must have a carbonyl. So the only way to put all this stuff together is to have your carbonyl, have the methyl on one side, and have the isopropyl group on the other side, like that. And there's the compound, just like that.